All right. So anybody, as we've gotten started, this is really the first meat and potatoes session for these classes. So at this stage, you should have gotten through chapters 1, 2, and 3. So if you're through 1, 2, and 3, you're on track. Obviously, you can go ahead, you can move forward in the process, but if you fall too far behind, then it's going to be problematic trying to play catch up. Everybody wait until the last week before the exam and try and do 6 chapters. So, all right. So, does anybody have any questions from the first 3 chapters? Things that came up as you were studying it that were a little bit unclear, or mistakes you think are in the book? You're all being shy here. Okay. Well, let me go ahead and I'm going to start up my paint here, and I'll try and review a couple of the concepts that I think are confusing. Not confusing, but if you don't understand them, they're so foundational that it's going to cause you some problems as you move on through the text. So the I'll reiterate, I think I probably mentioned at the last meeting, I don't believe any of these, nothing in this class or in this course is particularly difficult, but there's a lot of it. And it builds on top of itself. And at some point, you just begin to feel a little bit overwhelmed. That's normal. Um, Oh, some of the book questions at the end do not reflect the chapter quizzes. Yes. What you're dealing with there is 2 different editions of the textbook. Yeah, so the comment there is if you look at online, the questions on at the end of each of the online chapters are based on the 8th edition of the textbook. I haven't gotten it updated to the 9th edition. If you have the written 9th edition, there are additional questions, and the organization of the book has been reorganized a bit. So the book itself will not necessarily match directly with the online course. I hope to deal with that here soon, over the summer, but playing catch up on some of that. I think I sent you a link to the 8th edition, the PDF of the book. So if you really want to have them in harmony, you can look at the 8th edition. It's just that I wanted you to have the most current copy of the textbook available to you. So just, if you're willing to live life a little bit on the edge, right? That the questions are not going to match up exactly with what's on the online thing. They're going to be close until you start getting into the restructuring of the chapters. So bear that in mind. Okay, so I'm going to share the screen here. Does the final test? Yeah, the final test reflects the 8th edition at the moment, not the 9th edition. I would say that the main differences between the 9th edition and the 8th edition are we upgraded some of the illustrations, so that's nice. We reorganized some of the chapters. It was like chapter 7 was getting a little bit too long, a little too much material in there. So we broke it into a couple of chapters. And we did de emphasize lead acid batteries and emphasize the growth of lithium ion technologies. So, those are kind of the main differences between the 2 editions. Um, so, if you study the 9th edition, you'll be fine for the exam. If you study the 8th edition, you'll be fine for the exam. So everything that's on the exam is in both editions. It's just that you might learn a little bit more if you read the 9th edition. Hate to have you do that. Hate to have you have 50 pages of more material, but it's all there. All right, hopefully that answers that. Let me go ahead and share my screen here. I think that's going to work. And let me see. Are you guys seeing the paint? So, yep, okay, good. Somebody gave me a thumbs up. Everybody's so quiet. All right. So one of the issues that I want to sort of talk a little bit about, because none of this is intuitive, you're not born knowing this, is let's talk about the IV curve. So every solar panel has what we refer to as the IV curve. And the IV curve is just I for amps and V for volts. Now we use the letter I when we're talking about amps, when we're talking about it in the abstract. So if I were to write out the equation watts equals amps times volts, which is the power equation, I would use an I. If I say volts equals amps times resistance, which is Ohm's law, I would use the I. But if I wanted to say 60 watts equals half an amp times 120 volts, I use an A when you're dealing with a specific number. It's just the way we do it. And I didn't make this up. But anyway, so A, they don't use A, they use I for intensité de courant, but A you would use if you're dealing with specific numbers. You wouldn't say 0.5 I, it would be 0.5 A or for amps. All right, so each of these panels has what's known as an IV curve. And what it is it's just a graphic representation of what's happening with the power equation. Watts equals amps times volts. So I have amps, I have volts. If I chart it on a graph, I get watts. So the curve is just showing you what the watts are. Now this IV curve that you're given, and you don't have to calculate any of this, it's all given to you by the panel manufacturer. This is under standard test conditions. So the curve that you're given is under standard test conditions. And what are the things that are required for standard test conditions to exist? This time I'm going to require somebody to unmute and give me the three conditions that make up standard test conditions. I'll give you a hint. One's about temperature. We're going to have volunteers. You guys are going to try and outweight me. All right, let's see. I'm going to pick on somebody then. Okay, Morgan, I see you're unmuted. See, and I can actually see you, so that's good. So what three conditions make up standard test conditions? I'm actually not hearing you though. I'm still not getting you. How about Clifford? Can you jump in? Do you have a mic that you can turn on?
Irradiance, solar constant, and air temperature.
Okay, so the temperature, you're right. Temperature is 25 degrees Celsius. All right, that's not actually air temperature though, that's cell temperature.
Okay.
So, and then irradiance of 1,000 watts per square meter. And then the third one is 1.5 atmospheres. So basically, the sunlight is traveling through 1.5 atmospheres, which is essentially what you find at sea level in most of the northern hemisphere. So remember, all of these standards are written by, white guys with burr haircuts meeting in Paris, France, kind of thing. So, what is the situation? Well, when they were trying to come up with standard test conditions, the story is they were meeting in Paris and they said, okay, well, what's today? They go outside. It's about 25 degrees Celsius. That sounds like a good number. That's 77 degrees Fahrenheit. At sea level, you're going to get about 1,000 watts per square meter if you don't, if there are no clouds in the sky. And at sea level, at that latitude, you're going through about 1.5 atmospheres. Now, of these things, we don't really care about the atmospheres. That almost doesn't matter to us. What we really are worried about is temperature and irradiance. And I know it was mentioned there about the solar constant. The solar constant is basically what is the irradiance at the outside edge of the atmosphere. So if you go to the outside edge of the atmosphere, up where the satellites are, kind of thing, how much energy would be in the sunlight? Well, that's known as the solar constant, and it's around 1,360 watts per square meter. But what's funny about the solar constant is it's not constant. It varies over the course of the year. And why does it vary? It's because the Earth travels in elliptical orbit around the sun. So when it's further away, it's less. When it's closer, it's more. But it's around that. That's the average. So that leads a lot of people to say, well, why don't we stick solar panels up in the sky, because it's 1,300 watts per square meter, not 1,000, and the sun is always shining if we put it out there. And yeah, good idea, except it's expensive and doesn't make a lot of sense. I always say we do have space-based solar. It's called the sun. So why not harvest it here on Earth? So anyway, so we have a rate. This is what the IV curve is doing and is measuring. So under this curve, this is 0 at that axis point. So up here, this is the theoretical maximum amps that panel could produce under standard test conditions. And that's referred to as the ISC, the amps short circuit. It's the theoretical maximum amps. The theoretical maximum voltage is the VOC. That's the volts open circuit. So if I put a meter on the panel when it's not hooked up to anything, I'm measuring the VOC. Well, why do we care about these? Why do we care about the theoretical maximum, the theoretical maximum amps, theoretical maximum volts? Well, one thing you should note, what is ISC times 0? It's going to be 0, right? Anything times 0 is 0. So if the panel is operating at ISC, you're producing 0 watts. And if the panel is operating at VOC, you're producing 0 watts. So under both of these scenarios, you're not producing any power. So that's bad, right? You don't want to be operating at those extremes because you're not generating any power. So why do we even care? Well, when we design our system, we want to know what's the theoretical maximum voltage and what's the theoretical maximum amps. We're basically saying, I'm going to design my system for worst case scenario. Even though I know I'm not going to be operating there, it is theoretically possible to operate there. So for amps, we worry about amps when we're trying to design our wiring system. Because if the wire is too small to carry the amps, that wire could get hot, could, in extreme cases, catch on fire, could burn down your house if you put wire that's too small. So I'm going to say, okay, the maximum amps that panel could generate is the ISC. I'm going to make sure I design my wiring system to deal with the maximum theoretical amps. When it comes to volts, the National Electrical Code says that for residential, you can't exceed 600 volts for your system. So I'm going to design my system so it doesn't exceed 600 volts. Well, what volt am I using? I'm using the theoretical maximum voltage. So those two numbers I use when I'm designing my system because they're theoretically the biggest numbers that panel might produce. Now you'll find later that we've got to adjust it for temperature, but at the moment, just conceptually, just understand you're dealing with those numbers for design. Then somewhere along this curve, you're going to find a point where the maximum power is generated. And that maximum power point is somewhere here in the middle of that curve, and it's called the maximum power point, the MPP. or oftentimes it's referred to as the Pmax, but it's the maximum power point. So why is that not at VOC or ISC? Well, if we put some numbers to this, let's say that I put 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And just for simplicity, I'll say that this is 10 amps. And then we put over here and we've got 5 volts, 10 volts, 15, 20, 25, 30, and then we'll just say that's at 40. All right, so this is our thing. All right, so let's say that we start out and we're sending 5 volts over our system. 5 times 10, this panel is producing 50 watts. Then we increase the voltage to 10. It still hasn't changed much off of 10, so now it's producing 100 watts. Now we're at 15, and let's say it's at 9. So now the math gets more tricky for me to do in my head. I'll just say 9 times 15, 135 watts. Notice as we increase the voltage, the amount of power is increasing. So now we come to 20, and let's say it's at 8. So 20 times 8, 160. Now we're going here and it's at 25 and 7. So 25 times 7 is 175. Okay, so it's been doing as expected, but now after we reach a certain point, let's say we go to 30 and it's down to 40 watts or 44 amps, 30 volts. Now it's down to 120 watts. We continue on, maybe at 35, it's at 2. So it's at 70 watts. Here at, say, 27, and it's at 5. What's 27 times 5? 135. So see what's happened here is as we increase our voltage, it goes and it increases until we get to a certain point. Then it starts to decrease. And the analogy I like on this is to think of watts as the amount of traffic going through an intersection. And then as you add more cars, the amount of volts is the number of cars you're sending through that intersection. The more cars you add, the more traffic flows through that intersection until at some point those cars start to interfere with each other. And somebody taps the brake and then everybody has to slow down. And it keeps, so the more cars I add, the fewer cars actually go through the intersection until you get to VOC and you're at total gridlock. I've added so many volts to this system. I've added so many cars, nobody's moving. Everything's stuck. All right, so hopefully that analogy conceptually makes a little bit of sense. All right, so this point, the Pmax, or the maximum power point, so if this is being measured under STC and it's 175 watts, we would say that this is a 175 watt panel. So that's how we would refer to it. If you're going out and buying a 400 watt panel or a 350 watt panel, you're buying a panel that will generate 400 watts under standard test conditions at the maximum power point. Well, how do we know that it's going to operate at the maximum power point? Well, there is a little electronic device. I'm going to clean up some of this here. So there's a little electronic device inside in the systems, and it's referred to as the MPPT. That's the maximum power point tracking device. And it is a piece of electronics it's usually in the very first piece of electronic that connects to the panel. In a grid-tied system, that's usually the inverter. In a standalone system, it might be the charge controller. And now you're dealing with it automatically makes sure that panel is going to be producing at the maximum power point. It's a little adjusting. It's like a rheostat. As conditions changes, it's going to keep moving it so that that panel is producing the maximum amount of power it can produce under those circumstances. Well, when it's producing at the maximum power point, there is a voltage associated with that, and there is an amperage associated with that. The amperage is called the IMP or the Imax, and the voltage is the VMP or the Vmax. So this is where it gets a little bit confusing, because if I say the Vmax, your brain automatically assumes that's the maximum voltage. It's not. It's the voltage when it is producing the maximum amount of power. But the VOC is actually the maximum voltage. It produces zero power at VOC. So the 5 points that you need to know or understand is the ISC, the IMP, the Pmax, the VMP or Vmax, and the VOC. We use the VOC and the ISC when we're designing the system because they're the theoretically largest. And we use the Vmax or the Imax when we're trying to figure out how much power the system is actually producing, because that is the actual production. Does that all make sense? Any questions, any comments about this particular terminology?
So my question, I guess, is really more just electricity is not necessarily my strongest forte. Why couldn't you just keep why does it have to be a downward curve?
It's just the nature of a solar panel.
Is that just essentially like physics or like where the technology is? Like,
yeah.
Okay, cool.
Yeah, it's not something that we necessarily it has to do with trying to think the right word, but basically internal conflicts. So the more voltage you put into the system, the more that there will be internal conflicts in the electrical flow, which will then begin to reduce the amount of power output. Similar to traffic moving through a
right. So we're back to the traffic. Cool.
Yeah.
Okay.
All right.
Awesome.
So this is just given to you. When you look at a panel spec, you're going to see there's the ISC, the IMP, the Pmax, the VOC, the VMP. Then we're going to find we have to make adjustments based on temperature. But for the moment, you're just given these numbers. It's also important to know, and let me draw that. Remember, this is under standard test conditions. So what happens as temperature or as conditions change? Well, if this is my IV curve under standard test conditions, my curves are really bad. Okay, well, this is the ampacity here, and amps are primarily affected by irradiance. Well, under this, we're assuming that curve is 1,000 watts per square meter. Well, what happens if a cloud passes over the sun? Well, then suddenly the irradiance declines. It primarily affects amps. It does affect voltage slightly. So the curve may shift like this. Well, this may be the maximum power point at STC, but now that maximum power point is shifted to here. And if it gets even darker, well, that curve is going to be shifting again. And maybe the curve, maybe the maximum power point is adjusted there. And then what happens if it gets colder? Well, the cold affects voltage. The temperature affects voltage. It affects amps a little bit, but the colder it gets, the more volts it'll produce. So now our curve will shift out like that. So now our maximum power point's over here. Or what if it gets warmer? Well, then our curve may look something like that. So now it's over here. So the MPPT, the maximum power point tracking device, on a millisecond by millisecond basis is going to readjust that maximum power point to operate so that panel is producing the most power it can produce under the environmental conditions it's facing at that moment, right? So it's just doing the best it can given the circumstances. So you're getting maximum production out of the panel at all times. So that's great. And it really comes into play because in a system of multiple panels, let's say I've got a solar array here. And let's just, for simplicity's sake, say that I've got 8 solar panels, right? And they're all hooked together in a string. So all of these are going positive to negative, and so on and so forth. And then we come out of here, we go to a junction box. But all of these are connected together in one string. Well, what happens if, well, this thing, I'll just keep drawing it. From the junction box, we go to a DC disconnect. And from the DC disconnect, we go to the inverter. Well, in the inverter, you've got the MPPT. So it is going to determine that array is functioning at its maximum power point. But because all of the panels are hooked together, it's going to take the average, right? It's going to look at all of these combined and do the best it can based on the average situation of all 6 of those panels. Is that part clear? So what happens if I've got shading? Let's say there's a tree over here, and now this panel is shaded right here at the corner. And it turns out that shading, remember, affects amps. So let's say that under standard test conditions, it's generating 9 amps and 30 volts. Well, watts equals amps times volts. So 9 times 30, 270 watts. So if everything was happy, each of these panels would be generating 270 watts. We have 8 of them. So our whole array would be generating 2,160 watts. But now we've shaded this one panel. And this one panel, by shading it, has dropped this down to 2 amps times 30 volts equals 60 watts. And now every one of these panels is going to be functioning at the same output. 60 watts times 8. So by shading one little corner of that array, my production went from 2,160 watts to 480 watts. In the industry, we refer to that as bad, right? That's not good. You've just lost more than 3/4 of your output, 80% of your output, because one little corner is shaded. So what can you do? Well, in one situation, let's just make it simple. Let's assume we've got 4 strings coming in. So 4 strings of 2. And then we continue on with 4 strings. And then we have 4 MPPTs in our inverter. Well, then 3 of these strings are going to be behaving normally. So it'd be 270 times 6. They're unaffected by that shading. So that's going to be 270 times 6, 1620. This string is going to be affected, so it's going to be 60 times 2, or 120. So now we're at 1740. So by having 4 MPPTs, we were able to minimize the effect of that shading. Instead of dropping to 480, we're now just dropping to 1740. Still affected us, but not as dramatically. So what's a better solution? Well, let's put a power optimizer on each of these panels, an electronic device or a microinverter, and each of these little electronic devices that gets attached to this panel has its own MPPT. So now the only panel that's affected by shading is the one that's shaded. The other 7 are going to be completely unaffected by the shading of that one on that one panel. So this is why we would refer to that as a power optimizer, is it's optimizing the power from your array. Okay. So that's kind of where we're moving to. I know that I think this is in a future chapter, but another reason we're moving to this is there's a thing called rapid shutdown. I'm going to clean this off. And again, I know I'm giving you a lot of information here, but you can handle it. All right, so what is rapid shutdown? So rapid shutdown says, all right, I've got a building here, and I've got a solar array on top of that building. Up here, that's my solar array. Now, traditionally, what we've done is you've gone to a combiner box or a junction box. You've taken the wire. Let's say that we ran it under the roof. We popped it out of the side of the roof here at the eaves. We came down the side. We went to a DC disconnect. Then we go back into the building. Let's say we go down here and we go into the basement. And the reason I'm designing it this way is this, when I first got involved in solar, this was the normal way you did it. So we go into the basement, and then here is our inverter. It's down in the basement. And then from the inverter, we come out and we come up and we go to an AC disconnect. And that's going to be somewhere near your electric meter. And then from the AC disconnect, we go down into the basement. And here's your service panel. And we're going to connect into the circuit breaker box. And then this gets connected to the meter. And that's what you would do. Kind of cumbersome. But what happens? Well, the reason we put that AC disconnect out next to the meter is for the first responders and for the utility company. So if they have to come to your house and they have to shut off your system, they want that located out there near the meter so they can find it. So let's say that your house, it's the middle of the afternoon and your house catches on fire, right? And the fire engine arrives. What's the first thing they're going to do? They're going to come here to the meter. And typically what they would do is they would pull the meter. They would just pull it like it was a fuse, and you get disconnected from the grid because they don't want there to be any power in this building when they're fighting this fire. Then on the meter, there's a little sticker that says, hey, wait a minute, buddy, this house has a solar array. So they look around, and within 10 feet of this meter is the AC disconnect, and it says this is your solar array disconnect. So they walk over here and they turn it off. It's got to be well marked, and it's got to be externally operable. So now they've turned off your system. Well, what just happened is as soon as the inverter loses sight of the grid, it has a thing referred to as anti-islanding. And what it's designed to do is to stop generating power if the grid is not available, because they don't want to be backfeeding the grid if there's a power outage, because a lineman that's out working on the lines might get electrocuted. If you're generating power when he thinks the whole system is shut down, you could kill him. So they require, as part of the UL 1741, that these things shut off when they lose sight of the grid. So you've just shut it off. So it's stopped generating. But as long as the sun is shining, this array is still generating power all the way down until it reaches the inverter, because the inverter is where it's shut off. So all of these wires from the array across the attic, down the side of the building, through the DC disconnect and to the inverter, those are still hot. They're still live. So those are generating 600 volts of electricity, up to potentially 600 volts. So a fireman climbs up on the roof and he chainsaws through the roof to vent, and he hits this wire that is energized at 600 volts, and he dies, right? Bad idea. He thought there was no electricity in the building. He just cut through a live wire and he just died. So in 2014, the code said, hey, when you turn off this AC disconnect, we effectively want this to shut off at the array. We assume that these guys can see that there's an array up there if they're up on the roof, but we don't want there being any live wires leaving that array. That's basically what they said. And at the time in 2014, the industry, we were all going, how do we do that? We don't know how to do that. Well, one option would be take that inverter and stick it right up next to the array so that it shuts off at the array. Well, if you've got a 100-pound piece of equipment trying to stick it up on a shingle roof, it's not going to work. If you're installing it on a Walmart, on a flat roof, yeah, okay, that might be an option. But then company Enphase came up with a thing where they said, tell you what, instead of having one big inverter, let's put a micro inverter, a tiny little inverter, and let's attach each panel to its own little inverter. So we're going to do that up here on the roof. Every single panel is going to get its own little inverter. So we can put the MPPT on it so that every panel now operates independently. We can put the anti-islanding on it. So as soon as it loses sight of the grid, it shuts off at the panel. And how about if we also put communication so that I can monitor every single panel, and if one has a problem, I know which one it is, right? Why not put a little communication device in there? And then the other item is, let's do the inverter. Let's make it an inverter. Let's take it from DC to AC right there at the panel. So all of these wires leaving that panel are now AC 240 volts, which is what you need to run your house. So good option, right? Good idea. The only problem is each one of these inverters was like $250. And if I had 20 of them up on the roof, I'm looking at $5,000 for these little microinverters, and I could buy this inverter for like $1,500. So it's pricey. It was a pricey option. So then SolarEdge came along and they said, you know what we could do is we could put everything up here, the anti-islanding, the MPPT, the communication, we could put that in a little electronic device, but let's not do the inverter part. Let's have an inverter down here, but let's put all three of the other things up there on there. And so that was known as a power optimizer. And instead of charging $250 for that, we can just charge you $50. And the inverter, because now it's not as complicated as it was, we can charge you, say, $1,200 for that. So now, price-wise, maybe it's a better deal, especially the bigger the system. So we accomplished the same thing. So we had microinverters, and then we had power optimizers. As a result, today, Enphase microinverters make up about 60% of all of the systems installed on residential homes. Optimizers make up about 30%. And string inverters make up about 10%. So on a building, if I want to put in a regular old string inverter, I have to put in an anti-islanding electronic device on the panel. So companies like Tigo, they make little devices that, you know, for not much money, $20, you can put a piece of electronics on there. And you can get them with just the anti-islanding. You can get them with anti-islanding and MPPT. You can get them with anti-islanding, MPPT, and communications. So you can do whatever you want to do. But the reality is most of our systems are now microinverter and power optimizer. And that's the reason we do that, is because of that rapid shutdown provision. Now, there's one more thing I want to do here before we call it a day for this session. Hopefully I'll have enough time. Is I want to explain how the electricity flows through a system. And it's very different for a grid-tied system. So this is your array. Let's say this is your combiner box or junction box. And the only difference between a combiner box and a junction box is if you have multiple strings entering in and then you only have one pair of wires leaving, that's going to be a combiner box. You're making a parallel connection in the combiner box. A junction box just passes the wire through. And the reason you would do that is if your inverter has multiple MPPTs, you know, because if you combine them, you've now made the array just one unit. And so if one panel's shaded, all panels are shaded. So in today's world, we don't usually combine them anymore. We have a junction box. So from the junction box, we're going to go to a DC disconnect. In today's world, normally the DC disconnect is connected to the inverter. It's part of the same unit. It's got to be located within 10 feet, so why not make it the same unit? And then from the inverter, we go to the AC disconnect. That's got to be outside, near within 10 feet of the meter. From the AC disconnect, we're going to go into our service panel. That's your circuit breaker panel. We're going to connect into a double pole breaker. And then you've got the main, and the main goes out here to the meter. And from the meter, you're going to go up to the telephone pole where there's a transformer. And that's your system. Okay. Now from here, from your circuit breaker box, you're going to all of your loads, right? You're going to go to your kitchen outlets. You're going to go to your air conditioner. You're going to go to everything. Everybody clear about what we're doing here? All right, so how does the electricity flow through this system? So the first thing we do is if the array is generating power, that power is going to flow through the system, through the junction box, through the inverter. It goes from DC to AC. Now it goes through your AC disconnect, goes to your service panel, and electricity always flows to the closest load. Think of it like water finding its level. If you turn on a light, you've actually lowered the level, so the water's going to flow in. So the electricity is going to flow in from the nearest source. So the nearest source is your array. So it's going to flow in and it's going to service your loads. Well, what happens if there's not enough power being generated from the array to meet all of your load demand? Well, at the same time, power is going to flow in from the grid to your loads until all of them are met. So 100% of what's being generated from the array is going to service your loads. And then whatever else you need is going to come from the grid until that level has been found, until all your loads are met. So then what happens if the array is generating more power than you need? Well, under that scenario, I better get back to the pencil. It's going to flow and it's going to service the loads, but there's more power than what I need. So it's going to flow back through the meter and it's going to go to the grid. So if I'm generating more power than I need from my array, whatever's left goes to the grid. So where does it go? Well, it goes to the house next door. And then it'll flow into this house. Do they know or care that their power is coming from your solar array? No, they just get power. That's all they care about. All right, you get credit because it's running your meter backwards. That's referred to as net metering. Okay, so the whole point of this discussion here, other than just to understand how power flows, is how do we size the inverter, this device? Well, notice everything that comes from the array goes through the goes through the inverter, and it either services the loads or goes to the grid. So when we're sizing this, it's based on the size of the array. Does that make sense? If I've got a 10 kW array, 10,000 watts, you would think I would need a 10 kW inverter. It turns out you don't, but it is still based on the size of the array. There is a relationship between the array and the inverter. Is everyone clear on that?
I have a question.
Sure.
So when you're doing Enphase and you have more than one array and you have the little micro inverters when you're looking in the box, so each array would have its own full inverter then on top by the junction box? Or would they still only have one?
Yeah, if you've got inverters, or if you've got microinverters, then there's no need for another inverter. So if you're talking about multiple arrays
Yep.
with microinverters, right?
Yes, sir. Yes, sir.
All right, so let's just say that you've got 10 panels over here, and they each have a microinverter. So you would go from the junction box, and then let's just say for whatever reason, you've got another section over here, and there are 12. All right, 12 panels, and this is 10. And it just sort of happens, you've got two sections of the roof and you're doing two different things. Well, you'd have a junction box here as well. These things would be generating 240 volt AC power, right?
Yep.
So we would come from here, and then Enphase has another thing that they call the Enphase combiner box. And you would hook into a double pole breaker here and a double pole breaker here. And this is designed to handle up to 80 amps of input. Now, the proprietary cable from Enphase is limited to 20 amps. And it just happens, so this wire here has a maximum of 20 amps. So that just happens on normal to be 13 microinverters. So I could go with one here and one here. So I'm coming in. It's not going to be quite 40 amps, but the output of this is going to be 40 amps. This is going to go to your AC disconnect. And then that's going to go into your service panel. And so this is going to have 40 amps coming out. It's going to go into a 40 amp breaker over here. And then let's say that you've got 200 amp service. Then it's going to go out to your meter and so on. So you've basically combined in this combiner box. You could actually have 4 different strings coming in, 4 different arrays if you wanted to, combined, because this can handle up to 80 amps. Now they've also put the communication system in here. So your system is communicating through this unit. So that's Enphase. That's just how Enphase works.
So is that why there's 4 green dots when you look in one, and then they have to be lit up in green? You've probably seen an Enphase box or 3.
Are you talking about the microinverter itself or the combiner box?
Like, I'm talking about like the microinverter. Like you'll see like if you were to open up the box, the actual Enphase box, it has all the microinverters. It shows all the arrays. Typically, it has all the little numbers, and then it'll have like the actual system. It'll say whether it's communicating or not.
Yeah.
And is that the communication part, or is that?
Yeah, that's the communication part. So what
Okay.
that's doing, those little dots, and those are up in this inside. When you talk about opening the box, you're really talking about the combiner box. And there are like, I think 4 different dots up there. If they're all 4 green, everything's happy. If you get some amber, if you get some red, some of those dots are saying, are these systems communicating? Are they generating power? One of the dots is saying, am I communicating with the outside world through the modem? And then one of the other dots is, I don't know. There's different functionality, but that's basically the communication system.
Okay.
Now, on each one of those microinverters, there's an LED light on the side of it. And if you hook it up, if you go and look underneath, if that's green, that means that microinverter is producing. Everything's happy. If it's amber, it means it's producing, but it's not communicating. There's something wrong. Maybe your modem is down or something like that. And if it's red, it says just not working. So the only problem with that system is I can't tell the difference between amber and red when they've got those things up there. They're so close to each other. You almost have to have one that's red and one's amber to really know what you're looking at. So I wish they came up with a different, like maybe one's blue or something like that. But either way, maybe I'm partly colorblind. Who knows?
And then I have one more question for you.
Sure.
So why are systems always either mainlined or ran through a backbreaker? Like when you look at like the 200 volt, like how you have it on the 200 volt, and then you show it going to the 40A. Why are they always on the bottom? And why, unless they're mainlined right into that main switch?
Yeah. All right. Yep. Well, we're getting a couple of chapters ahead, I think, but I'll explain that. Because what you're dealing with there has to do with the circuit breaker box. So if you're coming in here, if this is your main, and let's assume you have 200 amp service coming in from the utility, then they have what's referred to as the 120% rule. So it basically says you cannot exceed the output of the bus bar or the capacity of the bus bar by more than 120%. So let me just explain what this means. Let's say I've got my 40 amps coming in from my inverter.
Okay.
Okay. Well, if the bus bar, which is the bar that runs down the middle of this that all the breakers are connected to, these have an electrical rating, just like wire does. So if the bus bar rating is 200 amps, and I have 200 amps coming in from the utility, and I have 40 amps coming in from my array, I've exceeded the capacity of that bus bar to handle electricity. But the reality is you don't turn on 200 amps of load all the time. You have that maximum, but you never turn stuff. I mean, you might, but it'd be rare. So the NEC said you can go up to 120% because we know that it has extra capacity. So, but if you do that, put the connection as far away on the bus bar away from the main as possible. And the reason for that is the electricity from here is going to flow up the bus bar and out. If you need more power, it's going to flow from here down the bus bar and out. So the power is not going to double up on itself and exceed the capacity of that bus bar. Okay, because we're coming at it from two different ends and feeding to the nearest load. So those are not going to double up on each other. So this is known as the 120% rule. And when you're installing solar into a circuit breaker box, this would be known as a load side connection. You want to make sure that you go as far away from the main as possible. That's not always a problem because usually the open spots are down at the bottom. You know, people just filling in from here. So you just go to the very bottom and you go into those locations. What happens if you have power output that exceeds that? Let's say I've got a really big solar array and I want to put out 80 amps. I don't have a choice. I can't load side connect it unless I decided to switch out my breaker and maybe put a 400 amp service panel in here. But if you've ever swapped out a service panel, that's going to cost you like $2,000.
Yes.
You know, it's a big chore. So your other option would be, okay, well, let's just not even connect load side. Let's come up here and tap in somewhere between here and the meter. And that would be known as a supply side connection. If you're on the supply side of the main breaker, that's a supply side. If you're on the load side of the main breaker, that's a load side connection. The further you get away from this kind of connection, the more expensive it's going to be because now you've got to hire an electrician. They've got to pull the meter. You got to shut down your electric. You've got to go in and put a splice in there and you've got to make that connection. So it adds cost. If you're doing it this way, well, shoot, all you need to do is just turn off the main. Now your box is dead. Wire up a 40 amp breaker, slap it in there. Once the connection's all made, turn the main back on, and you're all set to go. So it didn't require an electrician. It's a cheap and easy connection. But it's more and more unusual to find a service panel that has enough capacity and has enough open spots to make that connection. Because often if you're out there in the field, these service panels are just chocker block full, and maybe they were installed in 1970 and it's all crappy and all of that. So we'll come up with a different option. I'll give you a preview. Out at the meter now, the 2023 NEC now requires what they call an emergency disconnect, an emergency utility disconnect. And what that's saying is at the meter now, you've got to install what is effectively a small circuit breaker panel out there at the meter. And now this becomes the main, but this becomes a new place you could hook your solar array into. And you don't have to worry about the old existing wire.
I've seen them. The new ones have a little, and it even says solar on it. It's crazy.
Yeah. Well, it's required for new construction if you're following the NEC, but it's also required in many jurisdictions. You've got to upgrade to the newest code if you're doing substantial changes to your electrical system in the house. Well, installing solar, the inspector may determine that's a substantial change. So they're going to want you to put in a new emergency disconnect out at the meter. That's going to cost the customer some money. So, you know, these things aren't totally cheap. I don't know what they cost, maybe say $500, $600. but then there's the cost of install as well. So
Now, would energy companies do that, or would a regular electrician come out and do that typically?
yeah,
And
regular electrician.
okay, okay,
The utility's not going to do it. Um, the reality is, oftentimes solar companies will have an electrical guy on staff. They could arrange to do this. Um, I would recommend that you call the electric company, have them shut down the power. But I know a lot of electricians who put these things in while the power's live. I would never do it because I'm scared. But they do. They do. They've got the equipment. They've done it a million times. So, but it really does require an electrician.
now, would you call the one on your right supply tap because it's by the meter, or would it still be a load side?
It's still a load side because now this is the new main
Okay.
here. So you're still on the load side of the main. So it's still a load side connection.
But if it
But
was above that, it would be a supply
yeah, if
side.
you tapped in for some reason, I don't know why you would do it, but if you did it between the meter and the main, but yeah, that would be a supply side.
Okay.
Another thing to bear in mind when you do this, and this is kind of getting a little bit ahead as well, is in your main box, you're going to have a neutral bus bar and you're going to have a grounding bus bar, right? And
Hmm.
oftentimes, if you look inside, there's no distinction. In mine at home, I've got white wires going in there. I've got bare copper ground wires going in there. And the reason is because we bond these two together so the neutral and the ground are effectively the same thing. You're grounding your neutral wire. It's referred to as the grounded conductor.
Okay.
You can only do that in your main box, in the box where the main is. Any sub panels, these things are not connected together. They're separated. The ground and the neutrals are separated. There's only one place for making that bonded connection, and that's in your main disconnect panel. Well, if you add this box out here, it's now your main panel. And you're going to bond your ground and you're going to bond together the neutral and the ground.
Okay.
Well, if they're all intermixed in here, they've got to be separated. All of the grounds have to go to one bus bar, all of the neutrals have to go to the other bus bar, and any kind of connection between the two of them has to be disconnected. Otherwise, you're going to get a ground loop, and that causes interference in your electrical signal. So
What would you consider the definition of a ground loop?
it's just a situation where you'll get feedback onto your electrical. If you've got sensitive electrical devices, you may get some buzzing, some ghost images on videos. There may be some other issues out there, but it's a bad situation for sensitive electronics. Um, so just bear that in mind. If you put in or have someone put in a new emergency disconnect and that now becomes your main, they want to make sure that you've separated your neutrals and your grounds in any subsequent boxes. That's an electrical thing. It's not really a solar thing. The electrician should take care of that, but you should be aware of it
Okay.
because you're making yourself perhaps a problem. So, all right. Well, we've gone to the full hour. We'll do this again next Tuesday, but I appreciate your attention and I'll see you guys if you have any questions throughout the week. Don't hesitate to contact me and we'll call it a day. All right. Take care. Thanks.
Thank you.